Hello, we are Team Preah version 2. We would like to present a satellite project as a response to this year ISC 2024 problem statement. Our project title is a low-cost 30U MicroSAT mission to observe and gather mining data from two asteroids which are expected to approach near low Earth orbit in late 2026. To achieve this mission, we propose two scientific objectives which involve both topological and also compositional mapping of the two asteroids. We also propose one engineering objective to enhance our mining data collection. Next, we look at our mission design. To ensure that our JBSAT can successfully obtain all the required data types, we propose a three observation phases based on our objectives and instrument specification. First observation phase is a global observation. We mainly would like to know this asteroid physical property and also to understand their dynamic behaviors. Second, we have a mapping phase, which we are going to use two high accuracy instruments to achieve our complete mapping. Third, we do a detailed study on four selected sites to pass on all the significant data to the future mission. Next, it is necessary to analyze our propulsion system as it plays a key role to ensure that our JBSAT can sustain for all whole mission. We are using green propulsion system which has LPM-103S as its working propellant. From a setup orbital parameter as shown in table 3.1, we can obtain a delta V budget as stated in table 3.2. And our total delta V is around 15 km per second.
In order to accomplish our mission, we came up with our structure design for our spacecraft. The exterior of the satellite is shown here with the folding mechanism of the solar panels. To further scrutinize the structure, here we have an animated exploded view of the inner components, which include 5 payloads and other parts necessary for the spacecraft operation. From the structure, the satellite mass was calculated with every component taken into consideration. The frame is a 32U structure with a mass of 6 kg. The payload accounts for 3.1 kg. The thermal blanket has a mass of 12.96 kg. As for the electric power system, it has an overall mass of 7.14 kg. The sail drag system for the orbiting weighs 13 kg. The fuel and thrusters for cruising weighs 19.4 kg. And finally, the communication and the ADCS system weighs around 0.6 kg and 1.2 kg respectively. In total, all these components add up to an overall mass of 63.36 kg. In this section, we're going to introduce one of our main subsystems, which is our payload. The first payload is Gecko Imager, an optical camera providing RGB configuration. This camera is mainly used for navigation and surface mapping, and its main advantage is its high technology readiness level with space heritage. In addition, it is small in size, suitable for our spacecraft. The second instrument is the Gold Eye camera, an infrared camera actively used for mapping in dark areas of the asteroid surface. With great resolution and suitable wavelength range from 0.9 to 1.7 micrometer. The next payload is the Argus 2000 spectrometer, intended for compositional mapping by detecting a wide array of compounds and materials in the infrared range. The spectrometer has extensive spectral range and high spectral resolution, making it suitable for this mission. The fourth selected is the X123, used for compositional mapping in the X-ray range, revealing up to elemental composition of the asteroid surface. In addition, the X123 is minute in size and has low power consumption. Last but not least, the mission is equipped with a compact laser altimeter intended for navigation and topological mapping. This model is advantageous for its compactness and lightness compared to other models. In summary, 2 cameras, 2 spectrometers, and a laser altimeter are used as the payload subsystem for this mission.
As mentioned in the payload section, optical camera can capture visual image with rich detailed information, but it always faces some challenges in low light conditions. Therefore, SUR camera is used alongside to capture infrared image that is out of visible light range, but it is lack of richness of the information when it works alone. To solve this problem, an image enhancement method is implemented to improve the image quality by combining the visible and infrared image. It will go through two processes, which is the image registration, and it will follow by an image fusion. Figure 6.2 here shows an example of the image fusion when the visible image is taken in a low light condition. The result of the fused image have proven that the quality of image can be effectively improved using the image fusion technique when the image is not that clear in a low light condition.
It is crucial for satellites to work in low Earth orbit environment for a long mission. Therefore, our team present version 2 take this thermal fluid simulation in our consideration. Figure 7.1 presents our 3D model of our JBSat for this simulation, which we have done in ANSYS workbench software. After applying a professional meshing technique, we obtain a good quality mesh as shown in figure 7.2. It has around 3.5 million nodes and 2 million elements in total. After set up the input parameter as in low Earth orbit environment, we got a temperature contour as in this figure 7.3. It is noticeable that the instrument part, the maximum temperature is about 63. This shows that all our scientific instruments can work properly for the whole mission. Next, a key system for our JBSat. We are using a deep space network which is provided by Swedish Space Corporation. They have 10 ground stations globally as shown in figure 8.1. For the uplink, we use a S-band frequency, and downlink we selected X-band as we want to make sure that we can resolve all the data from our JBSat without any cutoff. And all the hardware we purchased from MicroSAT company.
The power system is an important system that regulates power. To manage the power collection and distribution, our team chose the EPS2 modular system provided by EndurSat due to its redundant power buses and resilience to radiation. It comes with a stackable battery pack with a capacity of 168 watt-hour. A power analysis was also done to find out how much power each mode uses. The sleep mode uses around 8 watt per orbit. The cruise mode uses around 167 watt per orbit. The safe mode uses 46 watt, and the normal mode uses 70.2 watt. By taking into consideration how much energy is needed to charge the battery, how much sunlight is present during orbit, and the efficiency of battery charging and solar array output, the total power that our solar panels would have to generate is calculated to be 284.1 watt. And since one 8U panel makes 24 watt, we would need a total of 12 8U panels. A finance analysis was also conducted. The costs were either taken directly from the product website, estimated from other similar products on the market, or estimated using the USCM8 cost model. The total project cost is estimated to be around 10.3 million USD.